Pressures are measured in depths, you would say, the height. Technically, that's not a pressure unit. Pressure is going to equal the density times G. Density in G is going to be a constant times the height for a particular system. Except for air, when we look at the column of air here, its density is going to change depending on how tall the column is. About how tall is the column of air? Does anybody know? Column of air. How thick is the atmosphere? 30,000 feet? 40, 50, 60, 100, 120? Whatever. It's going to be this column of air that extends all the way out here that's going to exert the pressure. So rather than talking about 30,000 feet of air, that's the pressure that we're sitting under, right? We equate it to liquids because liquids would have more manageable feet. And so if you have, let's say, 130,000 foot column of air here, that would be equivalent to how deep under a mercury pool would be. About 760 millimeters of mercury, or about how many feet of water? Maybe about 30 feet of water. Is that about right? It's a 3-story building. And so those are just ways of measuring the pressure. We're going to relate the pressure to a height or depth, and equate that. So at sea level, what is the average pressure roughly? At sea level around the equator, it's about 1 atmosphere, which is defined pretty much as 760 millimeters of Hg, which is going to equal 0.0317 how many?
0.0317.
Yeah, okay, 1.0 ... we could get it times 10 to the 5 pascals. Is that right? Which is equal to how many psi? 14.7? Psi, which is equal to, actually I should move this up here, which is going to equal
1.01.
about how many, if we have the 760 millimeters of mercury, how much water is that equivalent to? What was the density? 13.59 of mercury compared to water.
1 foot of mercury is 13.59 feet.
13.59 feet per 1 foot. Okay. And so if we do this, we have 760 millimeters of mercury. Mercury is very dense, and so we need 13 times the amount of water, 13.59. To check the density. That would mean we'd have 13.59 millimeters of water, liquid, for every 1 millimeter of liquid mercury. And so if we were under 1 millimeter deep of mercury liquid, that would be equivalent to being 13.59 millimeters deep in a water pool. And so this gives us how many millimeters of water this would be equivalent to. 10,000, 320. All right, 320 millimeters of water, H2O. And so that would be the equivalent weight for water, which would be, how thick is the atmosphere? I was supposed to check that this morning before coming in. 130,000 feet? Something like that? More? Well, let's just say hundred thousands of feet of atmosphere. Since it's very low density, so you're going to have to have that. And so here we see a height. This is a height. This is a height here, or depth. This would be a depth here. And, the height, length or height or whatever, depth, isn't going to match with a Pascal. You know what a Pascal is? A Pascal is a Newton per meter squared, which is an actual pressure unit. You know, and so this is just this relationship where we're chopping off the constants here, over there, and having these equivalent. A PSI would be pounds per square inch, so this would be similar to a Pascal in terms of force per area, unit area. All right, but us, we're pretty much going to stick with this. There's one other unit. You know, 1 atmosphere is about equal to 1.0 bar. Now, at least to 2 sig figs we'll get it. To 3 sig figs, it's going to be off a little bit. And so an atmosphere is about equivalent to a bar. A bar is 10 to the 5th pascals, basically. And so these are very similar units. And so often you'll hear, especially in metric systems widely adopted, bars and millibars versus millimeters of mercury and atmospheres. So we'll get some unit conversion problems in there as well. So the pressure, the temperature is your standard absolute temperature. Absolute temperature is on the what scale? Kelvin scale. Volumes, we could use any unit for volume, and then moles. So we come up with this relationship. This describes the physical properties of the gas. In terms of pressure, volume, moles, and temperature. This, everybody knows, is the ideal gas law. And the calculations, are they pretty straightforward? The calculations for this? Good. There are 2 things. One, density. You know, density is just mass divided by volume. And this is going to be density for gas. And so we know the volume can be calculated from the ideal gas law. The volume is just equal to nRT over P. And so we could get this. So we could get mass times P divided by nRT. But the mass over N, do you know what that is? Usually the units here, we put grams for mass and moles for N. And so that turns out to be the molar mass, which I'll abbreviate like this. We call this the molar mass of the gas. Times P over RT. So what this equation allows you to do is you don't have to do any experimental work to determine density. It's just a simple calculation. And so what we can do is we can calculate the density of a given gas at any temperature and pressure. T and P. And so we could do an example here of a sample problem. And I need to do. We're going to assume air is 80% nitrogen and 20% oxygen. It's off a little. It's more like 21% oxygen, something like that. But it also depends on what elevation you are. The composition changes, right? The higher the elevation, the more enriched in the lighter gases it would be. And so assume air is about 80% nitrogen, 20% O2. Calculate the density of air. Calc the density of air at, let's pick some temperatures and pressures. Let's pick a 25 degrees C. 25 degrees C we call RT. Do you know what RT stands for? Room temperature. At 25 degrees C in 1 atmosphere. And what else should we pick? Oh, sorry. 1 atmosphere. And let's pick another. Let's pick the density of air at. Okay, I'm going to go with, let's go with about 5 degrees C. 5 degrees C, will that make it more dense or less dense? It's going to make it more dense. And we'll go with 0.3 atmospheres. So maybe on top of Everest, I think it's about 1/3 of an atmosphere pressure. And the temperature maybe 5 degrees C, let's say. So let's go ahead and do that calculation now. So I need the molar mass, but you know, this is kind of a mixture problem here. And so how should I handle that? Should I calculate the density of the nitrogen and then calculate the density of oxygen and kind of try to figure it out from there? What should I do? Well, think about it for a minute and you tell me what I should do or how you would have handled this problem. What do you think the best approach is? And so I'll give you a minute to think about this. Now, should I do the graphical method? Should I do the, 2 equation 2 unknown? Or should I do something entirely different? Uh-huh.
Is it 2 equations when you add them up? If you do one for 80% nitrogen and one for 20% oxygen, you add up the density?
Yeah. You could do that if you do like a fractional.
Yeah.
Right. Remember when we figured out, well, we didn't do much for an example, but remember when you did these and probably did a lot of these in Chem 4, the average atomic mass is a weighted average, right? And so the air would be a similar thing. You know, it would be a weighted average, 80% oxygen, which is more dense, 20% nitrogen, which is less dense. It would be a weighted average. So you could do a weighted average. You would use an equation very similar to the equation you use for the average atomic mass. Fractional abundances of each. You do the fractional abundances of each of these. That's one way. The other way is we could use the graphical method. We assume that it's 100% nitrogen. What's its density? We assume it's 100% oxygen. What's its density? It's going to look like this, right? With oxygen is going to be more dense. With nitrogen is going to be less dense. At 80% nitrogen, 20% oxygen, it's going to be here. Does that make sense? So we could do the graphical method. We could do the algebra, like you said. But for gases, this is what we often do. We do a different method. For gases, when we have a gas mixture like this and we want the density, instead we calculate the average molar mass. Have you ever heard of the average molar mass? It's kind of a weird concept, but for gases it's okay because it's going to depend on average what does a mole of these particles weigh. If it were 100% oxygen, then a mole would weigh 32 grams. If it's 100% nitrogen, it would weigh 28 grams. Right? And so what we're going to do is we're just going to figure out the average molar mass. This is a different way of approaching. But we could use the other ways as well. It would work. And so here, average molar mass. This just gives you another way of solving. The average molar mass is, we have 20 out of 100 of O2. What's the molar mass of O2? 32.00 grams per mole, plus 80 out of 100 parts of 28.02 grams per mole. And this gives us an average molar mass of what? $28.8. Give me, we're allowed more. 28.816 grams per mole. All right, now these percentages are very rough. We can get a more accurate molar mass if we add the other components of air. What else is in air? Argon, helium, CO2, water. And so if we just have the list of components, we just tack on extra terms just like you would over here. If you had more isotopes, you just add the additional isotopes here. And so let's say, since these percentages are really rough, we really aren't allowed much. So it's about 29 grams per mole. Okay? And so I'm just going to do it to the proper sig figs. Really, these percentages are only good to maybe 1 or 2. So let's go with this, 28.8 grams per mole, or 29 grams per mole. All right, now once we have the average molar mass, then we can calculate the density, any temperature and pressure. The density of air, or this sample of air, which is simplified, is going to be the molar mass, which will do 28.8 grams per mole, times the pressure, which is, for the first calc, is 1 atmosphere, times the, what was it, PT temperature, which room temperature is going to be 298 Kelvin, divided by, is that right? Temperature is down. P, molar mass times P over RT, that's right. R is 0.08206 liters times atmosphere per mole Kelvin times T, 298 Kelvin. If we do this in bars, we have a different R constant here. It's just slightly different. And we wouldn't use atmospheres, we'd use bar. And so what does the density of air come out to here? $1.18. About 1.2 grams per what? Per liter. If you look at all the units, we end up with grams per liter. All right, let's go to the other condition. Density of air when we have, well, the molar mass doesn't change with temperature or anything else. The molar mass is fixed, grams per mole. The only thing that would change this would be varying the composition. Okay, times, now we're going to 0.3 atmospheres. 0.08206 liters times atmosphere per mole times Kelvin. Now the temperature, we want 5 degrees C, which would be 278 Kelvin. So this would be like the density of air on top of Everest, let's say. What would the density of air be on top of Everest? $0.378. Oh, we'll just go with that. 0.3. So it's about 1 versus 0.4 grams per liter. And so that's one thing about the density of air. The density of air changes dramatically as we get higher and higher, right? In terms. But for us, we're just going to assume, for small distances, like where we are, it's not going to change much in terms of the elevation. Small distances, that is. going up in elevation. Uh-huh.
What was the idea behind that? You find the average molar mass.
What was the idea behind finding the average molar mass? The idea was to show you yet another way of solving mixture problems. We would get the same answer if we did this. We use the graphical method. We assume 0% O2, 100% O2. And then if it's 0 O2, it's 28.02 grams per mole. If it's 100% O2, we get 32.00 grams per mole. And we know it's 20%, and so it gives us this. We would have gotten the same answer. No, actually, sorry. Wrong. If we would have done the density, it would have been, I would have been quicker to do the density. We would do the density assuming it's pure N2 under these conditions, and then we do the density assuming it's pure O2 under those conditions, and then figure it out. We get the same thing. And so, you know, what's the idea behind doing the average molar mass? It's something you can do for gas problems. That's all. Okay. And your book does it, so that's why we did it. All right, that's the. Okay, that's that. Now, we are going to come up with the next type of problem. And the next type of problem for this is to figure out the molar mass of the gas. The molar mass of the gas is just equal to the mass over the moles. Now, and we can use ideal gas law to figure out that. And so it's the mass divided by, well, N is equal to PV over RT. And so the molar mass of the gas can be easily calculated. This is the mass times RT over PV. And so what we have to do here is we have to weigh out a sample of gas. Weigh a sample of gas, which can be done, but it's a hassle. And then do the remaining calculations. Measure its temperature, volume, and pressure. Measure these. And so the utility of doing something like this is, okay, we get a sample of air, right? You get a sample of air, you measure its mass of that sample, the temperature, the pressure, and the volume, and we can calculate what the average molar mass of the air is. Just confirm it, right? You get some idea. Or if we have an unknown gas and we know it's pure, then we can just, gives us a way to determine the molar mass. Otherwise, how would you determine the molar mass of an unknown molecule? Is there a way to determine the molar mass of an unknown molecule? Experimental, doing what? No. With a mass spectrometer. Right, that's how you do it. Yeah, with a mass spectrometer, you can figure out. And so this gives us, if you don't have a fancy mass spectrometer, then you could do it if you have a big enough sample of gas. You know. Actually, there are even more ways of determining the molar mass experimentally. We'll talk about that. But one of them is like colligative properties. It has to be a gas for this. For colligative properties, you just have to be able to dissolve it in water. All right, then let's see, what else are we going to do? We're going to use the combined gas law as well. Well, for the combined gas law, we know that PV over RT, PV over NT, sorry, is equal to R, which is equal to constant. And so this allows us to solve for this equation. P1, V1 over N1T1 is equal to P2V2 over N2T2. And so this looks like the combined or universal gas law that you saw in Chem 4. The only difference is in Chem 1A, we might change the number of moles. That is, we'll force more moles of gas into the, or we'll suck moles of gas out of it. And so the number of moles might change from conditions 1 to conditions 2. But otherwise, the calculations are very similar. So take a look at those calculations in the homework. Maybe we'll do an example calc of that a little bit later. And so that's the combined gas law. And then after this particular section, we're going to look at gas stoichiometry. For gas stoichiometry, at the heart of the stoichiometry map, we have moles of A to moles of B conversion using the balanced chemical equation. And so with gases, we have different ways we can get there, as you're aware, I'm sure. We have volume of A gas. We can go volume of A gas to moles of A gas. There are two methods of doing this. The first method is just to go ahead and calculate it algebraically. N is equal to PV over RT. So we just calculate the number of moles of gas. The second way is we use something called the molar volume. The molar volume is equal to the volume to moles or moles to volume. And since we're calling it molar volume, we'll put the volume of gas A over moles of gas A. And so, in other words, we have V over N. V over N is equal to RT over P. And so what this gives us is this gives us units of liters per mole. Or if we flip it, we get moles per liter. A lot of people have the molar volume of the gas memorized, at least one of them. Do you have it memorized? The molar volume of the gas? Yeah, a lot of people have 22.4 memorized. Right, 22.4 liters per mole at STP. And so the example of this would be 22.4 liters per mole at STP. Standard temperature. What is standard temperature? 0 degrees C. And standard pressure? 1 atm. 0 degrees C and 1 atm. But the problem with STP is how often do you work inside a 0 degrees C lab? Never. And so what we're going to do is we're going to calculate the molar volume. This is going to be much more useful for us. Calculate the molar volume at RT and 1 atm. Okay, so MV will be molar volume. Can you go ahead and calculate that? Tell me when you got it. Huh? RT. You should know what RT is.
Oh,
Does somebody have it? Do you have it? What did you get?
24.45.
24.45.
We have 24.2.
24.2? 24.2 sounds wrong. 24.45 sounds right. 24.45 liters per mole.
What do you use for room temperature?
298 Kelvin.
There isn't temperature. Why do you stick to 50? It's supposed to be 275.45.
298.15 is what you got? 298.15? And what did you get for your volume?
24.47.
47? Well, you got this?
Yeah.
All right. 24.47 is what you got with 298.115. Okay.
Okay, so all the exam, it'll be have some of those you want to take off weights.
No, I want to take that. All right, so what we can do is we could do just a direct conversion from volume of gas A to moles of gas A. You know, sometimes though, we'll have mixture. And so we'll have a mixture of gas A, B, etc. Now, how are mixtures? You know, when I say air is 20% oxygen, what exactly am I talking about? Have you thought about that? Yeah. So gas mixtures, 20% O2 means what?
80%.
Yeah, 80% something else. But what does 20% O2? What can you tell me? Is it 100 grams of? Let's say if I had 100 grams of air, that means I have 20 grams of oxygen, 80 grams of nitrogen. By mass? No. For gases, it is not by mass. For gases, it's by molecules or by moles. In other words, if I had 100 molecules of air, 20 of the molecules will be oxygen, 80 of the molecules will be nitrogen. And so these are always mole percent. And so we say 20 moles of O2 per 100 moles of air, let's say, in air. Or 20 molecules of O2 per 100 molecules of air, which is the entire mixture. And so you have to memorize this because it's taken as a given. You know, you're supposed to have it memorized. Okay. Whereas, you know, others are mass percent automatically. This is a mole percent. Yeah. And so all we need is, if we have the mixture like this, if we have the volume of the mixture, then how do we deal with that? And so let's talk about that. If I have 20 moles, does this mean it's the same thing as 20 grams of O2 per 100 grams of air? No, that is definitely not true, right? But what about this? Does this mean that if I have 20 liters of O2, I would have 100 liters of air? Is that true or false? Or does that mean if I have 20 atmospheres of O2 for every 100 atmospheres of air? Is this true or false? They're both false?
Yeah.
Liters is okay, but atmospheres is not okay?
Yeah.
No?
We just found some other bottles.
This is true, this is true. But they cannot both be simultaneously true. So either only one at a time.
So how do you figure out?
Only one at a time. And so that's why we have to talk about this, gas mixtures, in more detail. Otherwise, you don't know in gas stoichiometry how to calculate what amount of A or what amount of B is in that mixture. Right? And so let's talk about gas mixtures now. We're going to take air, for example, here. Air's not difficult. One thing that's always true is this. One thing that is always true is, okay, if I take 100 molecules, then 20 of these will be O2. And so the mole percent is always true. This is 20% by mole O2, 80% by mole N2. Always true. All right, you said the liters is correct. So let's say I'm going to have 1 liter here of air. That means how many, if I separate out the nitrogen, how much nitrogen would I have? 0.8 liters. So I would have 0.8 liters of N2. Let's just take out the N2. And how many liters of O2? 0.2 liters. Put over here, 0.2 liters of O2. If I do this by atmosphere, okay, let's put some atmospheres here. I'm going to call this 1 atmosphere of air. How many atmospheres of N2 do I have? 0.8 atmospheres of N2. And how many atmospheres of O2 do I have? 0.2 atmospheres. And so we know about Dalton's law of partial pressures. 0.8 atmospheres of N2 plus 0.2 atmospheres of O2 gives us 0.8 PM. And so does this mean this is equal to 0.8 atmospheres here? Is that true or false? I have 0.8 liters of N2 at 0.8 atmospheres plus 0.2 liters of O2 at 0.2 atmospheres gives me 1 liter of air at 1 atmosphere. Is that true? No, it's false. Do you see they cannot simultaneously be true? In other words, here I'm going to have How does Dalton's law of partial pressure work? 0.8 plus 0.2 gives me 1. How does it work? Everybody knows Dalton's law is so easy. Add up the partial pressures to get the total pressure, right? But it doesn't work here. Maybe you don't see it because I need to show you how we do this. This is called Avogadro's law. Have you heard of Avogadro's law? Avogadro's law says that the moles and volume are proportional. So if you double the moles, you'll double the volume. Triple the moles, you're going to triple the volume. And so the volume of the gas depends on how many moles of gas you have. And so this is Avogadro's law. Avogadro's law says this. It says that V of the N2 plus V of the O2 equals V total. Here, let me erase this for a second. And what we have to have here is, do you see this box is smaller? Because we end up having one ATM, 1 atmosphere of O2 and 1 atmosphere of, N2 and O2. And so when we combine this, we get 1 atmosphere of N2 plus 1 atmosphere of O2 gives us a total pressure of 2 atmospheres? How do I get that? Isn't Dalton's law of partial pressure? I add up the pressure of the N2 plus the pressure of the O2 gives me P total. And so 1 plus 1 should give me 2. So why, do you see it's not going to work here? Or is it?
You need constant volume and temperature?
Right. This is what we call a gas mixture at constant pressure. So when we're thinking about constant pressure, if I take a 0.8 liter box of 1 atmosphere, add it to a 0.2 liter box of 1 atmosphere, I just put them together, I'm going to get a 1 liter box. That 1 liter box is going to be at 1 atmosphere. And so this is visualizing a gas mixture under constant pressure conditions. Visualizing gas mixture under constant pressure conditions. And so this way, when you have to be very clear, because if you have 0.8 atmospheres of nitrogen, right, you have to be very clear what you're talking about, because there are 2 ways of describing mixtures. You can describe a mixture under constant pressure conditions, and you can describe a mixture under constant volume conditions. If you describe it under one of those, then you can't cross-communicate. Because if somebody is visualizing this gas mixture in constant pressure conditions, and you're visualizing the mixture under constant volume conditions, you aren't going to connect. Right? Because you're going to be talking about 2 different things. This is going to be a mistake made. And so let's look at it under the same gas mixture under constant volume conditions. Under constant volume conditions, then how much N2 do I have? I have 1 liter of N2. Now, if I have a 1 liter box and it's just filled with pure N2, then I'm going to get fewer collisions, right, with the wall. And so this is just going to be 0.8 atmospheres worth, because there are no O2s colliding with the wall. And then I'm going to add this to a box that contains how much oxygen? 0.2 liters of oxygen? No, 1 liter of oxygen. 1 liter of oxygen. So if I have a 1 liter box of oxygen, there aren't that many molecules in here, and it's going to give me 0.2 atmospheres. So that 0.8 atmospheres plus 0.2 atmospheres gives me 1.0 atmospheres, or 1 atmosphere. And then 1 liter plus 1 liter gives me 1 liter. Okay, so what in Chem 4, you didn't have to deal with this because maybe it's too confusing, right? In Chem 1A, you have to deal with this because you're expected to be able to shift your frame of thinking from one side to the other. And even in certain problems, you know, actually we're going to do one, the decomposition of KClO3 lab later. You have to shift your frame of thinking. In one calculation, we look at it under constant pressure conditions, and then the second part of the calculation, we look at it under constant volume conditions. And so in one single problem, which is at a lab, we have to do calculations using both. And then you have to be very careful what you use for PV equals nRT, because if you use the pressure, you know, under, let's say, constant volume condition with the volume under constant pressure conditions, your calculation's screwed up. And people do that all the time, you know, because people don't keep track of this mentally. And so you have to keep track of this mentally. And so the way we do this is we come up with something like this to kind of help us visualize what's going on. And so, you know, 20%, let's go back to 20% O2 means 20 out of 100. 20 moles of O2 out of 100 moles total. This is called the mole fraction. This is the mole percent. The mole fraction is equal to the volume fraction as well. And so here, the volume fraction would be 20 liters of O2 for every 100 liters total. This is the volume fraction. Which is equal to the pressure fraction, 20 atmospheres of O2 for every 100 atmospheres total. So let's just reiterate. The mole fraction is unrestricted. It's always true. The volume fraction is not always true. The volume fraction is true only when constant pressure. True if constant pressure. The pressure fraction is true only when, yes, true if constant volume. So basically this will give us, anyway, whatever mixture of gas we're given with, we can deal with it. As long as we know this, we can figure out how much of that mixture is A, how much is B, right? All right, so that's some gas stoichiometry. I'll probably come back to gas stoichiometry. We'll do some problems after I cover the bulk of the chapter here with some sample problems later. After gas stoichiometry, then we're dealing with the kinetic molecular theory of gases. Whenever we think of a gas consists of mostly empty space. And they're tiny particles of, either molecules or atoms. Here. And these particles, they move in straight lines until they hit something and collide. Like that. So this is our visualization of gas, just a whole bunch of particles moving. And let's see. I'm going to show something. What else can you say about this gas? Do all the particles move at the same speed? No. And so what we have is we have a distribution of speeds at a given temperature. What does the distribution of speeds look like? It's an asymmetric bell curve. So the distribution of speeds looks something like this, where there is a high energy tail here. This would be the speed. Speed is also called velocity, and it's given different symbols like V or U. This is distribution is given by population on the y-axis and speed on the x-axis. Where's the average speed, roughly? Somewhere. Would it be the highest? This is called the most probable speed. The average speed is somewhere around here. Now, we have something called the root mean square speed. You know the mean, right? If you take the mean, what is the mean? Do you know the mean?
The median.
The mean is like, what is it? The average, I guess? The average. If you take the average, let's see if I can get a pen. So we have something called URMS. RMS stands for root mean square. This would be the root mean square speed. And when you just take the mean speed, which I'll call U bar, the average, square it and then take the square root. And you think, why do you square it and take the square root? Well, I don't want to get into a long explanation of this, except just to call this, if you take this whole collection of particles and gave it one speed, all of them, you know, what would that average speed be? And that would be the URMS. This would be what we call the effective speed of the collection of particles. The URMS. And this effective speed changes with the temperature. And so the temperature of the gas is directly proportional to the URMS speed. Is that correct? In other words, well, it's not really directly proportional. It's more complicated than that. You would think it'd be directly proportional to the speed, but actually it is directly proportional to something related to the speed, you know? It is called the kinetic energy, the average kinetic energy. It turns out that this is proportional to the average kinetic energy, which we're going to call E bar K. Now, what is the average kinetic energy? Well, the average kinetic energy is going to depend on the effective speed of this collection of particles. The faster the effective speed of the collection of the particles, the higher the average kinetic energy is going to be. And so the average kinetic energy is going to look like this. Just write it over here. The average kinetic energy is just going to equal 1/2 m u RMS squared. Or from physics, this would be 1/2 mv squared, one of Newton's laws. And so we take this whole collection, even though they're moving at different speeds, we're going to come up with some speed we're going to just call the effective speed of that collection. And then we're going to use that to calculate the average kinetic energy, which this is. Kinetic meaning motion. And average kinetic energy. And then we'll have it. And so the temperature is directly proportional to the average kinetic energy. And so what happens as the temperature increases? What happens as the temperature increases is the average kinetic energy should go up. And that means is the collection of speeds here should increase. The population, let's keep the population the same, the total population. And so what that's going to do is going to flatten this out. So we get a lower population of low energy and a higher population of higher energies. And so that's going to shift the URMS to the right here and thereby increase the average kinetic energy, and we should see an increase in temperature. The temperature you're going to feel from the collisions of the gas on your skin as it transfers the kinetic energy from one to the other. If we lower the temperature, lowering the temperature is going to increase the population of low energy and decrease the population of higher energy. And so what's going to happen here is the URMS decreases, therefore the average kinetic energy decreases and the temperature decreases. And so this would be a low temperature. Let's call this room temperature here, RT. And then over here, we'll just do high temperature, high T. Okay, this distribution is called a thermal distribution or a Maxwell-Boltzmann temperature distribution. So, or just Maxwell-Boltzmann or Boltzmann distribution. I shouldn't say temperature, thermal distribution, but you know, it's not a distribution of temperatures. Each one of these corresponds to just one temperature. The black is just one temperature. We have high energy, low energy. Collectively, we have URMS. This creates this temperature here. Now, we want to calculate some stuff. Calculating this distribution is not so easy to do. Although we can fit this, you know, we can fit this to some equation. We do a mathematical fit. And we can generate the equation of that distribution. But we aren't going to be generating the equation of this distribution and then doing calculations based on that. Instead, we're going to do some simpler calculations. And so all you need to know is just know the general shape of this. And how that shape changes with temperature. We aren't going to do any kind of mathematical fit for this, although it's not that hard. What we are going to do, though, is we're going to do some simple calculations. For example, the URMS. The URMS is just going to equal square root of the molar mass over RT. Is that right? So as the molar mass increases, what should happen to the speed? It should decrease. As it gets heavier, it's going to take more energy to push it, and so the speed should decrease, meaning that, is this right? I don't think so, because as the molar mass of this increases, the speed should increase. So I think what we have is, we have this equation, RT over the molar mass. So as the molar mass increases, the speed should decrease. Does this look right? Okay, but is there something else missing? This equation. Somebody help me out. Was it 4 RT? 3 RT? 3 RT would make sense because there's 3 degrees of freedom. This is where you can verify it. You don't have to have it memorized. In fact, I forgot it. Three RT. All right, so let's do some calculations with this. Let's calculate the URMS of air. What's the effective or collective speed of air at 25 degrees C in RT? And so, you know, if we treated all the molecules in air equivalently, what would their effective speed be? This equation, we aren't going to derive. This comes from the physics of this. It is 3RT because they look at the motion. It can go X, Y, Z. And then RT is related to the energy, kinetic energy. And so in other words, it's the, this is just URMS is equal to the E bar K, right, over the mass to 1/2. In other words, E bar K is equal to mass times URMS squared. But this is the form we're going to remember in.
Will this be given to us?
It'll be given to you on the test, so you don't have to memorize it. RT, you know, it's actually, I should have known, it's pretty easy to derive. RT is from the energy, translational energy of the gas. Do you know there are 3 kinds of motion? Did I talk about that? The 3 types of motion? A gas particle can translate across, you know, that is moved from point A to point B. But also it can rotate as it's translating, and it can also vibrate as it's translating. This is what we call an ideal gas. You know, in an ideal gas, do ideal gases rotate in space? No. Do ideal gases vibrate in space? No. And so if we're dealing with a real gas, a gas that can rotate and vibrate as it's translating, then we have more terms we add here. And so this is just strictly translational kinetic energy.
Specific type, like, is there units for this? Or?
There are units. That's why we're going to do a calculation for this. And so this equation is going to be given. Since the derivation of this is beyond the scope of the class. Well, anyway, UMRS of air, what do we need? That's just 3 times R. Now, which R do we use for this? Do we use the 0.08 or do we use the other one? Do you know the other one? 8.3145 joules per mole Kelvin? We actually have to use that. The R we're going to use is 8.3145 joules per mole Kelvin. And then T we have as 298 Kelvin. And then the molar mass is, what was the molar mass of air? 28.8?
Yeah.
Okay, grams per mole. Then when we look at the units for this, it doesn't work out at all. But if you know the definition for joule, then we're okay. A joule is equal to a kilogram meter squared per second squared. And so why don't you do this calculation, making sure all the units work out. So did you get it? $508? $508, what are the units you got? Meters per second. Okay, 508 meters per second. So 500 meters per second, how fast is that moving? That's fast.
How would you convert the numbers?
How do you convert grams to kilograms?
So, I mean,
How do you cancel them out?
um,
Well, you could convert it in your head. 28.8 grams per mole, you just move the decimal 3 places over. It's 0.0288 kilograms per mole. Or just, you divide by 1,000, kilogram per 1,000 grams. You just got to make sure the units work out for 1,000 grams. This type of calculation you can't do without writing the units and making sure they cancel out. There's a lot of mistakes are made without that. 508 meters per second, that's what, over 1,000 miles an hour? 1,000 miles an hour, isn't it? It's fast. It's air. A heavier molecule is going to move a lot slower, right? All right, so what we're going to do is let's do this calculation. Rather than doing URMS of air, let's do URMS of the nitrogen in air. Tell me what the URMS of the nitrogen in air is.
20. Oh,
The molar mass of nitrogen is 28.02 grams per mole. And then repeat the calculation for URMS of O2.
so for this, would we always be using the joules per mole over Kelvin?
Yes.
Okay.
You just make sure the units work out, and then you'll know which one to use. So does someone have the nitrogen?
Yeah, 515.
515. So the nitrogen is moving at 515 meters per second. The oxygen,
482.
482 meters per second. And so since the nitrogen's moving at 515 meters per second, does it have a higher kinetic energy than the oxygen?
No.
Because the nitrogen's moving much faster than the oxygen, and therefore it should have a higher kinetic energy. True? False, yeah. Right. The nitrogen, higher kinetic energy than oxygen. True or false? The answer is false. Why?
Same country.
Yeah, they're at the same temperature, and two, we have to factor in the mass. If both the nitrogen and the oxygen weighed the same amount, then for sure the nitrogen would have more energy. It's moving faster, but the problem is nitrogen weighs less. And so, you know, if you think about a truck moving 1,000 miles an hour hits you, that's some serious damage because the truck has a lot of energy, kinetic energy. But a nitrogen molecule moving 1,000 miles an hour and hits you, does it even phase you? No, it doesn't, because the nitrogen weighs so much less than a truck. And so let's do this. I want you to calculate E bar K for nitrogen and do the same for oxygen. E bar K is 1/2 MURMS squared. Get it to so that the units work out, and tell me what the units of the kinetic energy for nitrogen is, and tell me what the kinetic energy for oxygen is.
The same.
Are they about the same, or they're exactly the same? About the same? What is nitrogen's kinetic energy?
What is around 3,716
3,716 in the unit?
joule.
Joules. And a joule is a
16.58 something like
okay, 16.58. And what was oxygen?
that.
3,717.
17.18, something like that. Joules.
How'd you calculate?
How did you get those numbers?
How did you figure it out? How did you figure it out?
Just the mole mass.
That's this is huge. This is huge because you know why this is so huge? Because when we're thinking about the kinetic energy of a nitrogen molecule, we usually think in terms of a single molecule. And to have this much energy for a single molecule is enormous. And so this must not be joules, this must be joules for a whole mole of molecules. So this is just too big. And so the amount of energy I'm looking for is minuscule, it's tiny because it's just a single nitrogen molecule. And these kinetic energies are in terms of single nitrogen molecules. So let me go ahead and do this for the setup.
How did you get the joules?
Okay, and then we'll talk about that too right now. And so first thing is we want the mass of a single nitrogen. I know the mass of a single N2, that is 28.02 U. That's how much a single nitrogen molecule weighs, right? But I don't want U because the units joules, I want units of joules. Joules is kilograms. And so I need to go from U to kilogram to get joules, right? And so how do I go from U to kilogram? Well, I can go from U to gram easily. What is the conversion? Yeah, it would be 1 gram is equivalent to, all right, you have that one memorized, I have this one memorized, 6.022 times 10 to the 23rd U. Either one, just memorize one, or derive it. And so do you see the U cancels? And then I'm going to go to kilograms, that is 1,000 grams per kilogram. Okay, now I have the mass of a single molecule in kilograms. And so the grams cancel. So I need kilograms, and then I just put in the 515 meters per second and square that. And so I'll get kilograms meters squared per second squared, which is a joule. And since there's only one nitrogen molecule is not going to hurt me if it's moving at 515 meters per second and strikes my arm, right? That's not much energy. I mean, if you had 3,000, imagine 3,000 joules of energy heating up your arm. It's going to get very hot. And so this is going to be 6.17. Give me one more digit.
03.
617.0.
Times 10 to the minus 21.
Times 10 to the minus 21 joules. I expect numbers like this when dealing with a single molecule. You know, tiny numbers for tiny molecules. Okay, and then the average kinetic energy of O2 is equal to, just repeat the calculation rather, with 32.00 U. What is it? 6.173 times 10. You know what though? They're at the exact same temperature. If they're at the exact same temperature, then they should be exactly the same. But we aren't getting it exactly the same. Why? We aren't getting it exactly the same. Why is that? What do you think? No. No, even if one's bigger, it should be moving at the same energy. Not necessarily at the same speed, but the same energy. Round-off error. Where was the round-off? Where's the origin of the round-off error? Not this. Probably this is 4 sig figs. The velocity. We probably have round-off. If we carried all the digits in the calculator here, and then had this to more sig figs, then they should be exactly the same number. It's just a an issue of, all right, that's it for